Welcome everyone to the sequencing and pre-confirmations call number 4. Today we have a special guest, Brandon from Polygon, who will be talking about topics which are extremely complementary, in my opinion, to shared sequencing and base sequencing. Namely, the topic of cross roll-up bundle safety. So if you have a super transaction which involves multiple simple transactions on different sequencing environments, how do you make sure that they can all execute as a bundle? How do you make sure that you have safety without having to trust the sequencers or the sequencer in the case of one single shared sequencer? And I think Brendan will also talk about gas optimizations, which are very much relevant as well in the context of synchronous composability. Namely the idea of sharing deposits, so having one deposit contract for more than one roll-up. This is also something that ZK Sync has been thinking a lot about. And this other kind of maybe more obvious optimization, which is the idea of shared proofs. So if you have multiple roll-ups that share the same proof system, well, you can aggregate proofs, and you can also save gas there. Now, before we have Brendan on, I want to give a quick update on the based ecosystem. So as I see it, we now have multiple rollups that have either like committed to become a base rollup or are excited about it. So we all know Tycho, of course. One which is very new, and I've added to the slides just now, is Coinbase is building this minimal key value store as a base rollup. This is one of the ideas from Vitalik, and maybe we could have a presentation dedicated to that in the future. We also had a sequencing day in London, which was very well attended, and I think we've made lots of progress. In particular, we made a little mini breakthrough. So Ben Fish came up with this really clever idea to basically encrypt blobs to make sure that when a blob goes on chain, it cannot be associated with any given rollup. And actually that kind of really helps chains like Aztec that are sensitive to censorship. And so Aztec is now considering becoming a base rollup. And actually next week, we're going to have Aztec talk about base rollups and censorship resistance. We also have Rise, as I mentioned last time, which is a small rollup planning to become a base rollup. Then we have this mystery, like one of the top rollups in production today that is also looking into it. And then finally, while I was in London, I had chats with one of the ENS developers, and he was saying that they want to move to an L2, but they can't pick an ecosystem like Arbitrum or Optimism. And the reason is that they can't be in all the ecosystems at the same time. They have to pick one for the root of trust. And if they pick one, then they'll piss off everyone else. And so they have this very high demand for credible neutrality, which is why base sequencing is very attractive to them. Now, in addition to these rollups, we have various builders that are building infrastructure. And like, I think some of these builders behind the scenes, I've been having calls with some of you, like you're really stepping up your game in terms of building infrastructure around shared sequencing, base sequencing, pre-confirmations, all of that good stuff. And then like one of the other ecosystem players that I added is today for the slides is actually AgLayer, because again, this is infrastructure, which in my opinion is very complementary to this whole shared sequencing and base sequencing vision. So without further ado, I will give the floor to Brendan. We have a whole 55 minutes. So feel free to, is that okay if we interrupt you with questions?
Yeah, please actually interrupt me with questions. So so the presentation should be like, I don't know, 20 to 40 minutes. It's a big air bar, but yeah, if you interrupt me while it's going, and then I've built in time to discuss after as well.
Perfect. And I think Brendan will try and make the presentation like more technical, so we can like dive in pretty deep. And then after the hour, we have the usual half an hour kind of off the record conversation. So with that, Brendan, go ahead.
All right. Let me share my screen. Sorry guys, I just have to rejoin, so my Zoom permissions could be updated, but be right back. Sorry.
Okay, perfect. I guess while we're waiting, there's going to be more sequencing days organized. So at EFCC, someone is organizing a sequencing day, I believe. And I think there will also be a sequencing day at Zoo Berlin. So sequencing is becoming a hot topic. I'm actually not organizing either of these topics. I think Chris, do you want to give the 1 minute pitch?
Sure. So some of you might know Suzalu, which was organized by some people around Vitalik, and where we brought together different ecosystems for kind of a co-living experience in Montenegro. And then we had other spin-offs of that, SuConnect in Istanbul. And so after Berlin Blockchain Week in Berlin, we'll have a 2-week residency where we bring together blockchain researchers, but also AI people, neuroscience people, and kind of people just at the cutting edge of technology. And so it will be in June, from June 8th till 22nd. Roughly 100 people living together in Berlin. The possibility is to stay there for a week or for 2. And we'll have dedicated days for specific research topics around mechanism design, base sequencing. And yeah, there we're aligning with Justin Drake, with Barnaby, a few other researchers to organize one day, which will be on these topics as well. And yeah, zooberlin.city is the website. Feel free to pre-sign up there. And yeah, would love to see many of you there.
Thank you, Chris. And we'll also have a sequencing day with a different organizer at EFCC. Brandon, the floor is yours.
Okay. Can everyone see that?
Yes.
Cool. So yeah, so I'd just like to go a bit into the aggregation layer. So there will be 2 parts. The first part is high level and not very technical, and then the second part is maybe a little bit technical. All right. So the background, I guess, for some brief history of the ag layer, it arose from this problem that we had in Polygon that was very much a strategic one. We were working on like a multi-chain ecosystem, and we were wondering, like, how do we actually share network effects across many chains? So we had like the POS chain, and it had like, flourishing DeFi ecosystem, and it had liquidity, and we wanted to launch a zkVM rollup. And there was no real obvious way to actually share liquidity and for the zkVM rollup to benefit from what already existed on the POS chain. We needed to think about like bootstrapping liquidity and doing liquidity mining incentives and airdrops and kind of the same games that every L2 does when they start in order to like actually bootstrap an ecosystem on zkVM. And we realized that this was actually like a broader problem and like a more structural problem for Ethereum, where like it's actually very difficult for Ethereum to accrue network effects from L2s. I think that the like network effects tend to develop around specific L2s. So Justin brought up this nice term that Vitalik used for this, like the idea of mini empires that sort of like develop around individual ecosystems rather than around Ethereum itself. And so I think that this is not like, this is something that's very familiar to the people on this call. But I think fragmentation is a problem in 3 senses. So for users, it means increased complexity because you have to navigate like moving between chains and like accessing applications that are on maybe different chains from where your funds are. There's also a lack of safety involved here. So like often this requires third-party bridging, which doesn't offer the trust minimized guarantees that native bridging does for rollups. For builders, there's this issue where, like, if you are, like, let's say that you're building something that's really interesting and great. It could be like a new DeFi primitive or like an NFT collection or a game, and you're really, really good at building whatever it is that you're passionate about and you're setting out to build. But the problem is in order for you to be successful and launch your app chain or your L2, like, you not only need to succeed in building this thing that you have a comparative advantage in building, but you also need to succeed in like bootstrapping your chain. So you need to like for your NFT collection, build a marketplace and like bootstrap liquidity for that marketplace and like actually develop a chain ecosystem, not just sort of your individual application or this thing that you can actually have a comparative advantage in building. And finally, for Ethereum, this isn't great because network effects aren't shared. So like the success of an L2 ecosystem is like additive in some sense for Ethereum, but it's not like maximally additive. Like sort of we don't have this this like collaborative environment where like token incentives for one L2 benefit like all L2s and benefit the entire Ethereum ecosystem. And so I think it's like not an ideal like structural configuration for Ethereum. So again, this is I think very familiar for everyone on this call, but the goal is to unify Ethereum L2s. So by that, I mean two things. So we need to enable low latency composability, both asynchronous and synchronous. I think Justin is much better at terminology than I am, and he called this like super intense. So basically intents that span multiple chains in a single bundle. And moreover, you need to provide asset fungibility across chains. So if you're on one L2, you should be able to, in a very low latency way, like take your native ETH that's represented on that L2 and bring that to another L2 and get native ETH without necessarily going through the L1 and paying the latency penalty. So like in my mind, the technical barrier to this unification is like the reliance on going through Ethereum in order to use the native bridge between two rollups. So if we have like rollup A and rollup B, and let's say that they're both CK rollups, like there are a number of latency components that lead to a bad UX for native bridging between these two chains. So if you think about what's required for me to take like my ETH on Polygon zkVM and move it to zkSync or to StarkNet, I need to submit a withdrawal transaction on chain A. I need to wait for proof generation for the block that contains my withdrawal transaction. So this could take like 2 to 3 minutes and like a very fast and performant ZK rollup. It could take longer for others. I need to wait for like that batch to be submitted on L1. So right now, I believe that the lowest latency for batch submission is about 30 minutes, just to amortize the cost of proof verification on Ethereum. I need to wait until the batch or the block that verifies my proof is finalized on Ethereum. And so that takes like between 12 and 19 minutes. I then need to submit a deposit transaction to rollup B. That takes another 12 to 19 minutes for that block to finalize. And so finally, I receive tokens on B. And all in, this ends up being like a more than 25-minute latency penalty for a cross rollup transaction via the native bridge. Obviously, this is like the best case in an optimistic rollup. If you're using the native bridge, it's obviously much worse. So the AG layer is designed to solve this problem in conjunction with coordination infrastructure like shared sequencing. I think it's important to emphasize what the AG layer is not. So it's not an L2. It's not a shared sequencer. It's not just a proof aggregation service. So I think we'll talk about this later in the presentation, but I think there's this misconception that all that we're doing is aggregating validity proofs and that aggregating validity proofs gives the safety guarantee that we aim to provide, and that's not true. So when we talk about aggregation, we're actually talking about aggregating chains. So the ag layer, as I would describe it, is neutral public infrastructure that provides safety for asynchronous and synchronous cross-chain interoperability and a shared bridge. So again, aiming to satisfy these two criteria for unification. So cross-chain composability at lower latency than Ethereum finality, and asset fungibility via a shared bridge. And as Justin mentioned earlier, we're also able to massively reduce gas costs. So the ag layer works by accepting blocks from L2s before they're settled on Ethereum. And it proves like three things, I guess. So it proves first that cross-chain or cross-L2 transactions are safe, so they're consistent. That superintents and bundles are satisfied and are consistently included across chains. That interchain accounting is valid, and we'll talk about what this means exactly later. And finally, it does aggregate validity proofs. But again, it's really important to emphasize that this is primarily a gas optimization. So rather than needing to verify every single validity proof for every single L2 on L1, we can amortize the cost of proof verification across many L2s. So the ag layer vision is an ecosystem of independent sovereign chains. The ag layer does not, there's no element of rent seeking or extracting sequencer fees or profit. It does not require a specific VM or an execution environment. It doesn't place any limitations on the tokens the chains use. It doesn't require that they submit to common governance or that they use like a specific or prescribed shared sequencer or even a shared sequencer at all. Though, again, like the ag layer doesn't function without some sort of coordination mechanism between chains. So like the way that we think about it is that the ag layer is like this very, very minimal layer that provides the safety guarantees that we discussed earlier. And it works in conjunction with like a chain coordination layer. So that could be, again, a shared sequencer, a relay, builders, and so they're sort of like separate ecosystems that mutually depend on one another. So shared sequencers depend on the ag layer for safety. And then the ag layer depends on shared sequencers and this coordination, what we call like emergent coordination infrastructure, to actually navigate like producing cross-chain bundles and like performing the coordination between chains. So in the like universal, again, this is just to like sort of develop a very high level intuition about how it works. In the universal synchronous composability case, L2s would opt into using a shared sequencer. That's the only way that we know how to provide synchronous composability across chains. Users submit atomic bundles to a proposal or a proposer, and a builder would then execute and build blocks across many chains. And so then this is where it gets a little bit different. Like the chains would basically build their proofs in a certain way that allows the ag layer to check that the builder and shared sequencer built blocks in a valid way, and that the shared bridge was basically used safely, or like the bridge invariant was respected across all of these transactions. And so the ag layer submits these three proofs. Oh, sorry, yeah, Yuri, you had a question?
Yeah, could you explain a bit more the user submit atomic bundles to proposer? So far, so good. Proposer, user, bundles, make sense. Mm-hmm. And the builder executes builds block across many chains. Like I have like the chain is broken somewhere between the proposer and the builder here. Could you unpack it?
Yeah, so I might be using the wrong terminology here, but my understanding is that the idea is that after a bundle has been submitted to a proposer, that like some builder would then create the blocks across many different chains. And so this is required for synchronous composability, right? Because you need basically like all of those full nodes to be co-located, so you don't have to take locks that persist for a long time across many chains. And so that's just what I mean, that like the builder is actually producing those individual blocks for each chain. And then
okay, so we're kind of like glazing over proposer, builder, whatever. I don't really care about that. So like, okay, basically, user give a bundle of like, you know, actions across different chains or whatever, and then, you know, it comes somewhere between the proposer and the builder. Somebody creates a block so the proposer could create something along these lines, right?
Yeah, exactly. Like
okay,
just
then it's fine.
that like user sends off a bundle, and somehow we get like all the individual blocks created by chains. Cool. And so the AG layer then proves basically three things. It proves that these cross L2 transactions are handled in a valid way, so that like in the synchronous composability case, that there's no unbundling. That for every transaction, like if a bundle is included by one chain, then for every chain that is included in that bundle, the transaction on that chain executes successfully. It proves that the bridge invariant is respected. Basically, that no chain can withdraw more funds from, just withdraw more funds than are deposited on that chain. And then it provides an aggregated validity proof to L1. And so again, like this is just sort of like a very high level kind of like metaphorical view of the AG layer. It's like that very thin layer that's providing safety, upon which all of this like interesting and sort of rich coordination infrastructure can be built. So like shared sequencing, base sequencing, relays for asynchronous composability, like, but the AG layer is not providing chain coordination. It's just providing a safety guarantee so that users and chains don't need to trust this coordination infrastructure to behave in a valid way. All right, so I feel like we've run through the non-technical section, and we can get like a little bit more technical. So, so what do we mean when we talk about safety guarantees for cross L2 transactions? By safety, we mean that if two or more chains are interoperating at lower latency than Ethereum finality, then the chain, like, oh, sorry, Yuri, go ahead.
So just on summarizing the high level, the idea is that if I am a user and I want a few actions happening across multiple chains, some of them are cross-chain, I create the bundle saying, oh, here are the actions that I want to take. And I actually submit this to the different, or actually the shared sequencer of the different chains, right? So it's kind of like, and this lands on all of them. That's kind of like the high level. Okay.
Yeah. Which I think is consistent with, oh, go ahead, just.
So one thing that really helped me is that if I have a super transaction which cross two rollups, like rollup A and rollup B, I'm actually signing three messages. I'm signing transaction on rollup A, transaction on rollup B, and I'm also signing this super intent, which basically describes how I want the relationship between transactions A and B to work. And not only that, transactions A and B shouldn't be like replayable individually. And so there basically needs to be a transaction type with metadata that points back to the intent. And then what AG layer does is that it verifies the consistency of these transactions, these simple transactions with metadata, plus the signed super intent.
Yeah, exactly. And I think that that's not to detour too far, but I was actually speaking with Ben about this the other day. I think specifying that transaction type and exactly how it works is something that's still like an open item for this group. All right. So the safety guarantee basically says that like if I have a block from a chain, that block can be finalized on Ethereum, assuming that there's some cross-chain interaction that affects that block. It can be finalized on Ethereum if and only if the other chains that are, or its view of the other chains that are involved in that cross-chain interaction is consistent with what is actually finalized on Ethereum for those chains. So I think that we have the so like in the async composability case. So let's say that we have like rollup A and rollup B, and rollup A is sending a message to rollup B. And so obviously we don't want to wait for this message to be routed through L1 and for like the state of rollup A to be finalized on Ethereum because that would take too long. And so let's say that we want rollup B to accept this message from A before the state of rollup A is finalized on Ethereum. It could even be before a proof for A is generated. So we want super low latency cross-chain interaction, maybe on the order of like a second or under a second. But this can fail in a really bad way, like without the AG layer. So let's say that like rollup A creates a block, and it like let's say that it's valid. It could be invalid, but let's say that it's valid. And the message that's derived from this rollup block lowercase a is sent to B, and then B creates a block that depends on the message that it received from like block lowercase a. But let's assume that at the same time that rollup A is trying to like double spend or equivocate, and it sends A prime to Ethereum. And at the same time, chain B or rollup B sends this block B that depends on the state lowercase a to Ethereum. And so B has built a block that depends on a state that was never finalized, a state of A that was never finalized to Ethereum. And so this is really bad. Like B is rugged, like you can cause really bad things to happen on B. The bridge could become under collateralized, or there could be some like other kind of catastrophic issue that could occur. And so in the asynchronous composability case, the question is like, how do we provide safety in this case, even as we're operating at lower than Ethereum latency? So the really simple mechanism that we use to provide safety in the async case is, let's say that chain B receives a message from A that depends on block lowercase a, and then B builds block lowercase b. So in the proof for block B, we include a commitment to the received state of block A as a public input. And the idea is basically like B is valid if and only if block A is also valid, if there basically exists a valid proof for A, and if block A is finalized to Ethereum. And so we can think about like the role of the AG layer as basically receiving all of these new blocks and checking for consistency between basically like the claimed states about, or the like claims about other chains, and like what states are actually produced by those chains themselves. So in the case, like stepping back, in the case that this happens, like A equivocates and submits lowercase a to B, and then submits A prime to Ethereum, B would not be finalized on Ethereum. So there's a safety guarantee that like whatever invalid transactions B built that depend on a state of A that was never finalized, those will actually never be settled on Ethereum. So the downside, which we'll talk about later, is that there's a liveness issue for B because it built this block. Maybe it built like a bunch of different blocks that all depend on this state that was never valid or that never happened. And B will need to resolve that. But fundamentally, we are preserving the safety guarantee that if like the claimed state of A is never valid or is never finalized on Ethereum, that B will be safe from from settling an invalid state of Ethereum. So we can see in this slightly nicer diagram, like we have block B1 that depends on this other block A1. And so the AG layer is checking that for all of these sort of claims that that A1 is consistent with the block A1 that was actually received. So the more interesting case, I think for this group is like
Brendan,
case.
you have a question from Mirat.
Oh yeah.
So if you go back to the previous slide, so in that B prime block that doesn't get finalized, are we saying that there's a bunch of transactions that are basically invalid now?
Yeah, so they need to be reorged. So the transactions that depend on on an invalid or equivocated state of A would need to be reorged. And we'll get to like why this is like sort of an unavoidable property of or an unavoidable trade-off in operating at lower than Ethereum latency. But yeah, so B would need to navigate like A's misbehavior.
If you have two conflicting sets where, you know, A and B prime and then B prime and A, basically neither will happen, even though both were committed to.
So if A does not depend on a state that's invalid, then A would be finalized to Ethereum, but B would not be.
But if there's a second kind of transaction request where, you know, the inverse is basically requested for, neither will happen is kind of what we're pointing at here.
Yeah, yeah. I mean, A would never really do that because A knows that it's equivocating and that it's going to delay finalization of chain B. But yeah, in the example that you're giving, that would happen.
And would that be determined by like a first come, first serve? Like A wouldn't do that because his thing is before the other one?
Yeah, so if you're saying that like A is equivocating at A1 and then B is producing a block and then like equivocating back, then A knows that the block that depends on this equivocated block will never be finalized. So yeah. All right.
Hey,
John?
I just want to make sure I fully understand the concept. Maybe we can walk
Sure.
through an example with like
Yeah,
cross-chain swap, just to ground it in like a real example.
yeah, or like a burn mint. So like A decides to like, you know, wants to transfer some funds, and so they're burned on chain A, and then like a corresponding mint operation is triggered on chain B. And so let's say that like there's some transaction that burns 1,000 ETH on A. And so B says, okay, I've received this message, I can mint 1,000 ETH. And the problem is that if A now equivocates and finalizes a block to Ethereum that doesn't include this burn operation, then the like bridge for B becomes under collateralized in the case that there's no ag layer and that this can happen. Does that make sense?
Yeah, that was very helpful.
Okay, cool. Noah?
Yeah. Also, one thing I kind of want to point out with this is, and I think it's in the next diagram, is when if B1 is dependent on A1, and then there's a C1 that depends on B1, then you effectively have a tree of them all going up, where if A1 equivocates, then B1 would equivocate, and then C1 would equivocate there as well. So I think it's interesting to see. But I think that may be able to be mitigated depending on how it's set up. But the whole equivocating on the entire block makes it interesting because I think most of the examples in the past have been on individual bundles equivocating, not necessarily entire blocks equivocating.
Yeah,
so I think there's lots there that still need to be defined there. But yeah.
Yeah, I agree. I think that's a good thing to point out. And I would just say like this sounds like really bad. Like we could have like reorgs, liveness issues, like cascading reorgs, depending on like the dependency graph of like interactions between chains. But we'll see that this is basically like first of all, it's not as bad as it seems, or like it's not all that bad if you consider like what causes these issues. And it's like an inescapable trade-off at operating at lower than Ethereum latency. Basically, you can choose between having safety guaranteed or like trusting the coordination mechanism, like trusting a shared sequencer. But the problem is like if you just decide to trust the shared sequencer, then you have like no safety recourse if something like this happens. But Yuri, I think you had your hand up.
I'll say it this way. Does it make sense to think of it kind of like a merge between ZK rollups and optimistic rollups? Because you kind of like take take from ZK, like take the proofs from that, but you kind of like build on it in an optimistic way. So it's a bit of, it's not a rollup, but technically it's a bit of a merge between the two. let's get the proofs from both of them and kind of like work based on that, but we're optimistically working on that. Is that the right mental model?
Yeah, I think like we hesitate to use the terminology optimistic because I think it implies that there's like proof mechanism, so there will be like some challenge period, and that doesn't exist. But I think that you're right in the sense that like things are sort of like there's this window of uncertainty before like
yeah, maybe not optimistic, but kind of like unfinalized. But basically, we're kind of like using the ZK proof, etc., and working on that, even though they're not finalized.
Yeah.
So it's optimistic, not with proofs and everything, but optimistic in terms of we work on it despite not being finalized.
Yeah, I think unfinalized is really good. Is like a really good descriptor for it. Yeah.
Thanks.
All right. I'll just continue. So the synchronous composability case is I think a little bit more interesting. So you can have a bundle that maybe includes like a delta neutral arbitrage between two pools on different chains. And so like the user wants to remain delta neutral, and so like each leg of the trade should execute if and only if the other does. And so we create this bundle that has two transactions. It could have n transactions, but it has two transactions that execute across two chains. And the desired property is that like the transaction that executes on rollup A is included if and only if the transaction that is included on rollup B executes successfully. And so we have this like all or nothing guarantee that gives us atomicity. And so the failure would be that the shared sequencer in this case, or the builder, proposer, again, we're sort of like black boxing that, misbehaves and includes the transaction from the bundle on A, even though maybe the transaction that executes on B fails, or the shared sequencer doesn't include that transaction at all. But basically, like we have this unbundling. So we're no longer guaranteed this property that both transactions execute successfully. Instead, we only get like part of the bundle that's included on chains. And so this might not be so good if you're doing like a big trade or a big arbitrage in large size. You could be exploited by a malicious shared sequencer. And so in the past, the proposal has been we're going to collateralize shared sequencers, and then if they do this, we can slash them. So there's like an economic penalty for doing this. But you could imagine a case in which it's actually like profitable for a shared sequencer to unbundle transactions, because there's so much size, or they can like unbundle so many transactions or so many bundles that they're actually able to profit, even though they're being slashed and penalized economically. And so the idea with the AG layer at a very high level is let's provide a proof that all of these bundles or super intents were respected. So we can prove with the AG layer that for every bundle, we can look at every transaction that's included in that bundle and every chain that executes these transactions, and we can ensure that the bundle is included on all of these chains. And so if we assume that the chain validity proofs are sound, we enforce with the validity proof that if a chain commits to a bundle as a public input, then the transactions that execute on that chain must execute successfully. And so if the bundle is included or committed to by every chain, then we have a guarantee that all of the transactions in that bundle executed successfully. And so this is what the AG layer proves, is that these super intents or bundles are respected, and there's no way, like we have a cryptographic guarantee that they cannot be unbundled. So yeah, this is like a slightly nicer diagram, but
Brendan, maybe just maybe on the walk back to the last slide, and it might be just helpful to explain how, I mean, because this is solving a case where it's easy to make make two transactions not be able to be picked apart just using signatures. But the
Mhm.
failure case that you described without the AG layer is that some other transaction could be included on one rollup before that causes one of the transactions within these bundles to fail, right? So signatures allow for the bundle to not be picked apart, but it doesn't guarantee that both transactions will succeed, right? It could be the case that both transactions are executed, but one of them fails and the other one doesn't. So can you maybe explain how the AG layer, just so it's crystal clear, how the AG layer would prevent that, how the proofs are attestations over state, not just inclusion?
Yeah, exactly. So like Ben said, the shared sequencers give you a guarantee that the transactions are included, but not that they execute successfully, because there's no like claim about validity or state. And so in this case, every chain that include like the AG layer checks that for each bundle, that all chains that are involved in that bundle actually commit to that bundle as a public input. And then the validity proof for each chain guarantees that if a chain is committing to a bundle as a public input, that all transactions that execute on that chain, as well as like all transactions that execute on that chain must execute successfully. So we actually have this guarantee that the state of a particular, or that we have a guarantee about like the outcome of a transaction, not just its inclusion. Is that like a little clearer about?
Yeah.
Okay, cool.
I think maybe going to walk through the actual details of how the proof works, that could make it even more clear.
Yeah, so like for the AG layer proof, or for the ZK.
Yeah, like what exactly is the proof that's happening from each chain, and what would cause this proof to be invalid for all the chains if one of the transactions in the bundle failed?
Yeah, sure. So the AG layer proof is basically just checking that it looks at, like, it iterates over every bundle, and then it builds a list of chains that are included in that bundle, and it checks that each of those chains' validity proof includes that bundle as a public input. And so we know that, like, in some sense, the bundle is included across all of those chains. And then we have a guarantee from the individual chain validity proof that if the bundle is included as a public input, it looks at the the transactions that are included in that bundle that are executed on that specific chain, and it guarantees that those transactions are executed validly. So this is like a modification of the standard ZK-VM proof to accept a new type of public input. And it enforces that if there's a value in this public input, that like this specific property holds, which is that a transaction that's included in the bundle must execute successfully on that chain. And so if you think about like the result after we've iterated through every bundle and every transaction, we have a guarantee that like the bundle cannot be unbundled, because we have a guarantee that all transactions in the bundle executed successfully. Does that make sense?
Yeah, and specifically the transaction only succeeds on one of these rollups if the proof ultimately is valid, and that can happen if all the other transactions also succeeded on the other layers.
Yeah. So the AG layer will like reject an unbundled transaction. All right. So I think Justin.
Yeah, I mean, going back to Ben's question, in my mind, the distinction is not between inclusion and execution guarantees. Like a shared sequencer can provide promises on either, whatever they want. The real distinction is on cryptoeconomic guarantees versus cryptographic guarantees. So if you don't have the AG layer, the best you can do is have the shared sequencer be collateralized. And if they don't honor their promise, the intent of the user, then they get slashed. Whereas here it's a stronger cryptographic guarantee where the bundle can't get unbundled.
Yeah.
Well, but I think it is from a user's perspective a difference between So execution atomicity and inclusion atomicity. So from the shared sequencer's perspective, it can certainly guarantee any atomic outcome that it wants over the states of the chains, and then it can make a promise on that. But Brendan is handling the case that a user is submitting a bundle. A user doesn't trust the shared sequencer, no matter how collateralized it is. So it doesn't want a promise from the shared sequencer. It simply wants a guarantee that the bundle will not be unbundled, and that's something that ag layer additionally enables. I think we're saying the same thing.
Okay, gotcha. Sure.
Okay, George. I think George just disappeared from my screen. So maybe.
Oh, sorry, I was muted. I was muted. Sorry.
Yeah.
You said that transaction. So essentially, the proof is guaranteeing not only transaction inclusion but also the transaction outcome, which is like a portion of the talk that we just had. What's the way that transaction outcome is specified? Like, how do you specify like the specific outcome when it can pretty much be dynamic?
Well, so you're specifying the outcome that you're specifying is that the transaction executes successfully. That's like the only guarantee that we care about for atomicity. We don't care that it executes in a specific, like that it has a specific result. I think it's really difficult to like I think that there are cases where you can guarantee that like you could create an intent that a transaction has a specific result or like falls within some like slippage range, but in general, I think it's difficult to like construct that arbitrarily.
If you have a single shared sequencer, it's pretty possible because they can they control the pre-state. Whether this is cryptographically provable beforehand is, I guess, another matter.
Yeah, so I'm thinking. I thought you meant from like the user's perspective, like a user's ability to like specify an output state. I think is difficult in general. It's you can do it in certain cases, but yeah. Anil?
Yep, just a quick clarification. So when A agrees to have a block small a as a part of public input, are they providing any economic guarantee if they equivocate and submit A prime, or that guarantee is provided by ag layer?
So yeah, so I think this is a good question. Like whether a chain should be collateralized in some way so that if they equivocate, then they could be slashed. Or I think that there are arguments for both. Like there are ways to like seriously penalize chains for equivocating, even if they're not collateralized. So you could like remove them from the ag layer, and chains could opt not to accept messages or bundles that involve them. But yeah, I think that's like sort of out of scope and still we're sort of like punting that decision to the chain level. So I think chains get to navigate like the trade-offs that they're willing to make in terms of using shared sequencers and like using relays, like accepting asynchronous messages from chains that where they may not have a proof for. And so yeah, so I think it's a good question. It's a little bit out of scope for this particular discussion, but thank you. And Mohammed.
Yeah, I have a question about what's your mental model, or what's the right mental model to think about the aggregation layer here? So is it correct to think about aggregation layer as just one extra proof that checks the consistency of like different proofs of this like rollup A and rollup B, and like what you're describing here is just the way that consistency check or consistency proof is structured, and that's it, like, or like it has additional components to it?
Yeah, so it has additional components that we'll get to, but from the perspective of ensuring safety for cross-chain interaction, I mean it's producing a proof that gives a cryptographic guarantee that the chains are behaving in a valid way and that like the total state of all chains is consistent.
Yeah, I have a follow-up question, like and it's more about like developer experience, like from the perspective of developers. So for instance, I can if I have synchronous composability, I can imagine like one transaction on rollup A making a smart contract call on rollup B, like with some new opcode, like say X call or cross call or something. And that would that like second call can like happen or not happen depending on some state on rollup A.
Mhm.
Would something like this be still possible here, or is it going to have like too much overhead if one leg failed or something like that?
Well, so the only way that can fail, right, is if the chain or the operator of the chain is actually misbehaving. Like whoever's in charge of attesting to that a particular block or state is canonical is actually lying and equivocating. And so yeah, so I think that what you're describing is sort of the use case for developers. We call it bridge and call in Polygon. So it's the ability to like bridge funds and then like call some function on the destination chain. And so I think that that's the intent for this design, is to be able to do that safely at lower latency than Ethereum. Anil, did you have a follow-up question?
No,
Anil,
sorry, I
you
have a
muted.
follow-up question. I just raised hand. I need to lower it. Thank you.
Okay, thanks. All right, so I'll continue. So the second component, to get more directly to Mohammed's question, is like we need a shared bridge to enable asset fungibility for L1 and L2 native assets. So we need to avoid the requirement that when we're bridging assets between chains, we either get a wrapped synthetic on the destination chain, which is not ideal because we need to swap out of it and we need liquidity for the native token, or we need to go through L1. And so what a shared bridge or a shared deposit contract allows us to do is we can take like ETH, like the L1 native representation of ETH, and we can bridge it to a different chain in this ecosystem, and we get ETH, like the native bridge representation of ETH. And the way that we do that is by having a shared bridge and shared deposit contract. But there's a problem here, because we also want to enable permissionless, heterogeneous execution environments. So anyone should be able to deploy like, a type 1 or type 2 zkVM, or for us, like Polygon Maiden, or like the Solana VM or the Move VM. Like there shouldn't be any restriction or sort of governance process for you to deploy an execution environment for your chain. But the problem here is, like, when we're just using a single VM, we have a reasonable guarantee that that prover is sound. So we might have done a bunch of audits, and we might have formal verification, and this like pretty high degree of confidence that there are no soundness issues with that prover. But as we add more provers to this ecosystem, and more provers that are plugging into the shared bridge, then the probability that there is some soundness issue across all of those provers goes up pretty dramatically. And that's not great, right? Because if we have a shared bridge, now if there's a prover with a soundness issue anywhere in the ecosystem, then that prover could create a transaction that, like, say, mints like 1 million ETH and drains the entire bridge of all funds deposited into the ecosystem. And so this is, like, obviously a very bad catastrophic outcome. And it's something that we need to avoid. So the solution is, like, the second cryptographic guarantee that the AG layer provides is that it tracks aggregate token balances for each chain. So it says, okay, on ZKVM, there's maybe 10,000 ETH or something that's deposited in the chain, and some amount of USDC, and so all these tokens are tracked in aggregate for each chain. And when a chain submits a block or a batch to the AG layer, we look at what we call like the local exit tree of messages. So these are all of the asset transfers that are coming out of that chain, and we parse all of them, and we ensure that the withdrawals do not cause the chain to go negative. And then we are able to I think it's the next slide. But we basically like recursively build the cumulative deposits that flow into each chain, and we use that to update this data structure that holds the aggregate token balances for each chain, and we call this the interchain or chain level accounting proof, or the invariant proof. And this allows us to give a guarantee that like even if a particular prover is unsound, it can't withdraw more funds than are currently locked in that chain. And so we're able to mirror basically the same guarantees that would exist if that chain were just like directly posting proofs to L1. Like if you have an unsound prover for any ZK rollup, then it can drain the funds that are deposited directly to that chain, but it can't drain the funds that are deposited to any ZK rollup on Ethereum. And so we are mirroring that guarantee by ensuring that a chain cannot withdraw more funds than it currently has. And so this is different. You can think about this as like a proof that lives alongside the validity proof for a chain. And unlike the validity proof, which is basically arbitrary, it can be sort of like any execution environment, and it might be sound or it might be unsound. The interchain accounting proof is something that we specify. And it's a uniform circuit that's applied to every single chain. And so the AG layer does depend on this to be sound, but it's a much, much simpler proof, and it's compatible with any arbitrary execution environment. So what are the sort of failure modes here? From the perspective of the AG layer, like we actually just are effectively assuming that that validity proofs aren't necessarily sound, if that makes sense. But from the perspective of the users of these chains, obviously the soundness of validity proofs matters a lot, because if you're on a chain with an unsound prover, your funds can be rugged by an attacker or a malicious operator, creating an invalid proof that mints a bunch of tokens and then withdrawing all of those tokens. There's also a second issue where users can still be rugged or have their funds stolen if an attacker compromises an unsound chain, or sorry, if they're holding assets that are L2 native assets that are issued by a chain that has an unsound prover. So the attacker could create a transaction, like maybe you have an ERC20 with like a fixed supply, and the attacker could create an invalid transaction that mints a bunch of that ERC20, and uses that to basically like reduce the value of the tokens that you hold. And so from the perspective of the AG layer is still safe with respect to unsound provers in aggregate. But the soundness of validity proofs matters quite a bit for users. Yeah, go ahead, Ben.
Oh yeah, just so you are, this whole like discussion here is because you want to be able to support participation in AG layer from ZKVMs that have different proof systems. Am I understanding correctly?
So not, it doesn't even have to be different proof systems, but different like different provers. So you could imagine like
well,
like
then I didn't understand what you mean by an unsound proof.
Just like a ZKVM that allows that's not sound with respect to like the ability for an attacker to generate a proof that verifies for an invalid transaction.
So if they're sharing the same proof system, why would
the different
some
circuit, for example, the
Yeah,
circuit
yeah,
would have a bug?
Yeah, so like
I see.
yeah, like you could have like a bunch of like Plonky 3 ZKVMs, and one of them has a bug and would allow you to
The bug would be in like the circuit. The circuit is incorrect for representing the transaction validity. I see.
Yeah, exactly. Yeah, maybe the terminology is not quite right, but like an incorrect implementation of the prover for an execution environment.
But Brendan, one of the top voted questions in the chat is like, do you support multiple proof systems? And I think the answer is a resounding yes. The whole point is that anyone can come permissionlessly register their verifier circuit with an arbitrary proof system, like arbitrary SNARK circuit. And if they get rugged, well, all the deposits get rugged, but not the deposits of other chains because of this interchain accounting.
Yeah, exactly. And sorry, I know that there are a ton of, I'm not sure how to see. Oh, okay. I can read the chat.
I don't think it's worth it. It's way too much in there for you.
Okay.
Continue with your presentation. Yeah.
Okay. All right. So hopefully that makes sense. So basically, like the two, I think like material and interesting cryptographic guarantees are around cross-chain consistency and then this interchain accounting. Okay. Someone, Kalman had a question.
Hey. So I was wondering if you saw the last Preconfirmation calls 2 weeks ago. We also presented a very similar idea. Basically, I think it's essentially the same idea. The difference was we were focused on doing this on layer 1, and this would allow interoperability between different ecosystems. As I understand, this idea is only works if you're using the AG layer. So if you're in the Polygon ecosystem, shouldn't we do this on a wider Ethereum level?
Yeah, so you can definitely, I think it's obvious that you can do it at L1, but like, yeah, I mean, we came up with this a long time ago, but the goal is like you should be able to interoperate between chains without touching L1 at all. Like that's how we can scale and how we can like reduce gas cost and latency significantly, because otherwise, if we're routing things through L1, then we not only pay gas cost penalty, but we're also paying a latency penalty.
Yeah, but if you settle the proofs on layer 1 of what you call interchain accounting, what I last time called asset verifiers, then you similarly wouldn't have to go through layer 1.
Yeah, so but I'm not clear, like if you're going to go between ecosystems, you're just saying like do all of the accounting on L1. I think that would be really expensive to
No.
Okay.
I'm saying that you are proposing the shared bridge, which holds all the funds and is secured by this asset verifier, basically. So why have this on what is an Polygon AG layer 2? Why not have it on a layer 1?
Because that would be incredibly expensive.
So, Brendan, I think Kalman is asking a different question, sorry. So I think what Kalman presented and what you presented for shared deposits is actually like basically the same idea, where you have one contract where everyone makes deposits, and one of the things that you gain is this gas optimization because you don't have to go through the L1. I think what Kalman is asking is this a Polygon AG layer or is this an Ethereum AG layer? And I think the answer, this is an Ethereum AG layer where anyone, even beyond the bounds of the Polygon ecosystem, can opt in.
Yeah, exactly. So this is not supposed to be like specific to the Polygon ecosystem.
But you have to use the Polygon AG layer to opt into your interchain accounting interchain accounting. So I was wondering why not?
Well, so we don't call it like the Polygon AG layer. We just call it the AG layer because like there are a lot of like so yes, you have to use this thing that we are currently engaged in building. But it's not meant to be like a Polygon specific piece of infrastructure.
Okay, but you know, other ecosystems might also have a proof aggregation, like Starkware already has their shared prover. So I'm wondering why not put this interoperability solution that solves fragmentation on layer 1 instead of on this chain.
Maybe I'm just being like super dense, but I don't really see how that would.
Okay, then let's discuss this later, maybe.
Yeah. Okay. So Jonas.
Yeah, I want to echo a chat. Thanks for the talk, by the way. I want to echo a question in the chat from Cooper. Like, who's running the ag layer, and kind of are there rollups that opt into this, relying on liveness for these people that are running this, or how does it work basically?
Yeah, so it's run by a decentralized network of nodes that are generating proofs and providing this guarantee. The liveness and censorship mechanism is not discussed in this presentation, but there are ways that I think you can very straightforwardly force inclusion or have some mechanism on L1 that would allow you to avoid using the ag layer itself.
Can I tag one to Jonas's? What are the actors that are running ag layer being paid? Like, how are they recouped for their uses?
Yeah, so there would need to be some mechanism where they would be compensated for the cost of generating proofs, but these proofs are like very, very, very light relative to, say, like a validity proof for zkVM. So this is like a very, very nominal fee.
Are these actors separate from the L1 proposers?
I think that I haven't thought about that. I think that they would. I'm not sure if they could be the same. They could certainly be like using, you know, E3 stakers or something like that. But
is there any requirement for timeliness or censorship resistance on the people that are doing the aggregation, generation, and then submission into the various rollups, and I guess that one?
Yes, definitely. So they need to generate these proofs in order for batches to be finalized on Ethereum, and so there is like a timeliness resistance element. Yeah, Ellie.
Yeah, sorry, maybe I missed this, but with this interchain accounting, would this require that the nodes in ag layer like are able to execute across all of the different VMs?
No, because the only information that they need is in the list of asset transfers that's included with every batch, and so it's not like random stuff crazy stuff could be happening inside each VM, but those actions produce a result that's uniform across chains.
Okay, I see. That makes sense. Thank you.
Sure. Ben, I think you still have your hand up, but that might be in error.
Oh yeah, that's definitely an error. Sorry.
Okay. And I realize I've gone like way over time, but I think we're basically, so it's maybe worth discussing like the ag layer failure modes. So I think it's really important to emphasize that like if chains are using a shared sequencer, we can have these like nasty liveness issues where like the shared sequencer well, yeah, maybe it's better in the async case. Like if we have like messages and there's like equivocation or there's some issue that prevents finalization of one chain. It's really important to emphasize that this, like if we didn't have the ag layer, we wouldn't have these liveness issues, but we also wouldn't have safety. And so the impact would just be that like the shared sequencer or some like misbehaving chain could steal funds from another chain. And so like we are adding a safety guarantee. We're not like introducing the possibility of liveness issues or faults. If that makes sense. Yeah. So this basically requires ZK because if you're using an optimistic rollup and the latency of your finality for your native bridge is super long, then the dependency graph of and like possibility for Leibniz faults and reorgs like increases dramatically. But yeah, I think we can pause there, and if there are any lingering questions or discussion, or we can just transition to the off the record discussion as well.
Perfect. Thank you, Brendan. We're going to end the call here and then start the off the record discussion now. Thanks again, Brendan.
Yeah, of course.